Solid oxide cell devices are of great interest for efficient and clean power generation and for highly efficient conversion of electricity to hydrogen, fuels, and chemicals using high-temperature electrolysis. The cells targeted by BEST4Hy consist of a lanthanum cobalt-rich perovskite cathode, an yttrium-stabilized zirconium electrolyte, and a nickel yttrium-stabilized zirconium anode. The BEST4Hy project aims to develop an effective recycling process for the selective recovery and reuse of ceramic materials from end-of-life solid oxide fuel cells.
At first, after the removal of the sealant, the end-of-life cell is immersed in distilled water to scratch the cathode by means of a metallic spatula and recover the lanthanum and cobalt-rich perovskite in the form of powder. The excess liquid is removed and the powders are dried in an oven overnight.
Meanwhile, cathode residuals are polished away from the half cell to guarantee the purity of the materials recovered from the anode components. Both dried cathode powders and fragments of the polished anode cell are placed in a grinding bowl and milled in a planetary mill for a few hours. After that, the milled powders are sieved below 20 micrometers to improve the effectiveness of the recovery process. The milled anode powders are hydrothermally treated at 200 degrees inside a steel reactor to boost the recovery of nickel and yttrium-stabilized zirconia. Hydrothermal conditions further disaggregate the sintered powders, maximizing the surface area. The disaggregated powders are recovered through centrifugation. The powders are then treated to selectively extract nickel from the composite while preserving the yttrium-stabilized zirconia structure. Upon acidic treatment, a nickel-rich green supernatant solution is obtained, along with white yttrium-stabilized zirconia powders. Yttrium-stabilized zirconia powders and nickel-rich supernatant are separated through centrifugation. Now, yttrium-stabilized zirconia is ready for cell remanufacturing, while the green supernatant is further processed to obtain nickel oxide. Oxalic acid is added to the supernatant for the precipitation of nickel oxalate. Sodium hydroxide is added to adjust the pH of the solution. The precipitate is then separated through centrifugation. Afterwards, nickel oxalate powders are calcinated at 450 degrees to induce their transformation to nickel oxide. Yttrium-stabilized zirconia and nickel oxide are successfully recovered from the anode components of the cell.
For the cathode, a leaching process with nitric acid is performed on the sieved powders to extract lanthanum and cobalt. After 3 hours, a pink dispersion rich in lanthanum and cobalt is obtained. Through centrifugation, the pink cobalt and lanthanum rich liquid is separated from the residual yttrium-stabilized zirconia. 2 sequential precipitations at different pHs are performed in order to selectively recover lanthanum and cobalt precursors. Firstly, oxalic acid is added to the solution to determine the precipitation of lanthanum-rich oxalate powders. Sodium hydroxide is added to adjust the pH. The powders are separated from the cobalt-rich supernatant by centrifugation. Again, oxalic acid is added to the cobalt-rich supernatant. The pH is adjusted with sodium hydroxide to reach the optimum value for cobalt precipitation. All leaching and precipitation processes presented are advantageous in terms of energy consumption as they are carried out below 80 degrees. Cobalt-rich pink oxalate powders are separated from a green liquid. Lastly, lanthanum and cobalt oxalate hydrates are calcinated in a furnace at 410 and 750 degrees, respectively. Lanthanum and cobalt oxides are successfully recovered from the end-of-life cathode.
The full set of obtained powders are characterized in terms of crystallinity, size, morphology, and specific surface area in order to confirm their suitability as raw materials for solid oxide fuel cells remanufacturing.